Hello and welcome to another video on orbital mechanics. I am going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition, and I'm up to problem 2.24. And problem 2.24 is saying a satellite is launched into Earth orbit at an altitude of 1,000 kilometers with a speed of 10 kilometers per second and a flight path angle of 15 degrees. Calculate the true anomaly of the launch point and the period of the orbit. So we have an elliptical orbit, and let's say this is our focal point, and it says that the flight path angle is 15 degrees. Now the flight path angle is the angle that it's running to the perpendicular, so of your radius. So that's r, that's the perpendicular, and this here, that's the flight path angle, right? So we're given the velocity, which is 10 kilometers per second, and we're given that this is actually equal to 15 degrees. So we can easily work out the v azimuth, velocity azimuth, and the velocity radial. So the velocity azimuth is just going to be v times cos of 15 degrees, and the velocity radial equals v times sine of 15 degrees. And when we have the velocity azimuth can be related to the angular momentum, so the angular momentum, and this is in the book, and you know, it's well-known angular momentum formulas. So r, we are given r, and now we have the velocity azimuth. We can get the angular momentum, and then from the angular momentum we can get the semi-major axis, which is r mu over, and this is a rearrangement of, this is just rearranging v equals square root of mu over 2 over r minus 1 over a. Rearrange that to solve for a. And then once you have a, the semi-major axis a, you can get the eccentricity, which is the square root of 1 minus h squared over a mu. Again, just rearranging equations. That one is that one rearranged. You want to get the angle. Sorry, yeah, I want to get the angle. So the angle is cos inverse 1 minus e squared a over r minus 1. This is a really bad. So this is fine. We'll go with this. It's a bit of an ugly equation. It could be simplified a bit better, but it does work out in the end. So that gives you theta for your true anomaly, and it also wants the period of the orbit, and the period is t equals 2 pi a 3 over 2 over square root of gravitational constant, and then convert that into hours. Yep, that is everything for 2.24. If you have any questions or you think I've made a mistake, leave them in the comments, and the MATLAB will be in the description below. Thank you. Bye-bye.